The absolute bedrock principle governing all concrete mix design is the water-to-cement ratio. The physics are strictly proportional. Minimizing water content creates a dense internal matrix, which maximizes the final compressive strength of the concrete. But that structural density comes with an immediate physical consequence. A low water mix is rigid, resists flow, and is difficult to consolidate perfectly on a job site. Conversely, adding excess water guarantees excellent workability. The mix pours easily and fills forms without effort. However, as that volume of water evaporates, it leaves microscopic voids, degrading the final structural integrity. This graph visualizes the paradox: water-to-cement ratio on the x-axis, while compressive strength and workability curves intersect at a central compromise zone. Zooming in reveals the physical gap between the maximum theoretical strength and the practical workability required to pour it. Traditional mix design is inherently a zero-sum game. Engineers often sacrifice ultimate structural strength simply to achieve practical placement. The standard industry fix for this limitation is to use chemical superplasticizers, additives designed to artificially boost flow without adding water. But these chemical admixtures have limitations, particularly when applied to high-wear or massive flatwork pavements that demand rapid placement and deep structural stability. The central engineering tension remains: achieving fluid consolidation across a massive area without sacrificing the heavy molecular density of a dry mix. Vacuum dewatered flooring, or vacuum concrete, provides a mechanical solution to this problem. The core mechanism of this system is to intentionally utilize a high water-to-cement ratio for initial placement, and then physically extract that excess water before the concrete cures. By utilizing this fluid mix, the concrete surges over a dense rebar grid, demonstrating high initial workability and effortless placement. Vacuum dewatered flooring decouples workability from final strength, breaking the historical paradox by solving the placement problem first and the density problem second. The process begins by pouring this water-heavy, highly workable mix onto the site. Rigid C-channel formwork acts as a physical boundary, containing this fluid volume accurately along the pavement edges. Once the volume is contained, a double-beam screed vibrator is deployed across the surface for initial leveling. As the screed passes over the mix, its aggressive downward vibration forces the heaviest stone aggregates to settle deep into the formwork. This downward settling triggers a physical displacement. Excess fluid, known as bleed water, is pushed upward toward the surface of the slab. This 3D cross-section maps the internal migration. While the dense aggregate particles sink to the bottom, the displaced bleed water is forced upward to pool across the entire upper surface layer. Without immediate mechanical intervention, this pooled water will eventually evaporate, leaving behind structural voids and a surface layer prone to failure. To prevent this, a specialized hardware stack is layered onto the wet concrete immediately after the screed finishes leveling. The first layer of this stack is a specialized filter media that descends directly over the wet concrete surface, making contact with the pooled water. This filter mesh operates under strict tolerances. It allows pure water molecules to pass through while physically blocking fine sand and cement paste. Next, a heavy, impermeable section mat is draped entirely over the filter media, covering the footprint of the pour. A 4-inch gap is carefully maintained and secured around the entire perimeter edge of this suction mat. This perimeter seal is an absolute requirement. It prevents atmospheric air from leaking under the edges and destroying the negative pressure environment needed for extraction. With the hardware in place, the open concrete slab is transformed into a hermetically sealed, pressurized containment vessel ready for fluid extraction. A high-capacity 3 to 5 horsepower vacuum pump is then connected directly to the sealed suction mat assembly and activated. Operational timing here is strictly enforced. The system must sustain negative pressure across the slab for exactly 15 to 20 minutes. The moment the pump turns on, it evacuates the trapped air from between the mat and the slab, creating a powerful pressure differential. Looking at an extreme microscopic cross-section, negative pressure pulls water droplets up through vertical capillary channels, while gray cement particles hit the horizontal mesh barrier and stop. This artificial vacuum induces rapid upward capillary action, pulling water out from deep within the concrete matrix. The filter media acts as a physical dam. The fine aggregates pack tightly beneath the mesh, allowing only the pure water to pass through the top layer. That extracted water is continuously routed out from the mat assembly and deposited into an external water separator unit. In just 20 minutes, this mechanical extraction rapidly drops the final water-to-cement ratio post-placement, achieving an internal structural density that natural evaporation simply cannot. Immediately after the vacuum pump shuts down and the mats are removed, the concrete surface is rapidly hardened and exceptionally stiff. A heavy power trowel spinning rapidly over the semi-dry concrete surface is then used to oppressively smooth the rough top layer. The mechanical function of this power floating step is to utilize raw kinetic energy and intense downward weight to compress the newly dehydrated top layer. This final downward compaction permanently closes the microscopic capillary channels that were left open by the escaping water. By sealing those vertical escape routes, power floating converts the dense internal matrix into an impenetrable surface shield, engineered to withstand severe external abrasion. The ultimate metric of success in civil engineering is the intersection of required curing time and total structural strength. The universal baseline timeline for standard concrete mixes requires a full 28 days to reach peak compressive strength. This horizontal bar chart contrasts the curing timelines. While the top bar tracks a standard mix reaching peak target strength at 28 days, the bottom bar tracks vacuum concrete hitting that exact same peak target strength at the 10-day mark. Compressing the curing schedule by 18 full days offers significant logistical, scheduling, and financial advantages on large-scale civil sites. Beyond speed, the extreme density of the final matrix yields vital environmental resistances, including tolerance to severe temperature swings, rapid freeze-thaw cycles, and heavy weather. This combination of rapid curing, maximum density, and wear resistance is why this technique is required for airport runways, highway pavements, and deep industrial basements. By utilizing mechanical physics to bypass the core paradox of material science, vacuum dewatered flooring elevates standard concrete into a high-density structural medium.